structure inside your life is how typical North European weather, rainy and windy and ugly. I like it so much.
Hello.
What is it? Recording. Live cast.
Sound working? So sound is working, yeah?
Alright, thank you for changing to yeah. So this one is a very nice project. Very interesting. What is? I saw when you were it is a very interesting.
Yeah, inherently.
Hello,
My name is Rich.
I'm Costa.
Costa.
Nice to meet you. You are from the defense, right?
Yeah, I'm one of his friends.
I'm a colleague of you.
Okay.
We're
You work
in the
at-
same
work
lab.
at them?
Yeah, I'm not together, but yeah, in the same group.
Okay.
Yes.
Absolutely.
No. We have 1 minute for the official stuff, but I think it will take some time when the people say something.
You know where my closest restroom is for?
If you continue the corner, you will see it.
Okay.
Cool. We're be doing a couple cast lectures in the operating system. Oh, really? Yeah. Oh, okay.
We were on two.
Okay. Yeah, it's like, okay. Yeah, so-
Hello,
What's up?
how are you?
Long time no see. Pretty good.
I am Greece.
Go on.
In a week. And, I am started this.
You fine?
Yeah.
You're 13.
Vegan. How about you?
I've been around.
You go somewhere?
Been around. Been here. Trying to pass calls.
Oh, yeah.
That stuff. I get some water real quick.
Yeah.
But every food, but I hope every food.
No.
This will do. It's gonna be a lot of this.
And just like so.
This is black one. I think.
Hey, man.
What's up? Come on, these out to do.
No. What are you doing? But how do you get out these snacks? Oh, my water.
What the pre-game?
Yeah.
My previous lab, it was like a fasting when I was at the birthday, I was bringing a cake. And we were done and we were eating this cake and then everyone was going up to the room. At some point, one guy said, yeah, I brought a cake of the earth. And everyone said, okay, that's not fruit. And everyone was extremely disappointed because they were thinking, chocolate cake or fruit cake. And what is this?
Can help you.
Yeah,
It's
it's a cake of the earth. No.
This is a distance learning room, so they actually teach courses here and then record and broadcast with interactive cameras and whatnot.
No war yet, right? No war yet.
no wall?
War.
War? Oh, no wall, no war.
Yeah. And the long flight I was thinking, what is happening right now? It's 7 hours flight, it's 9 hours flight. This can change.
If it all be there.
Yeah. No, the mediation over there. I have my visa, but I need to have a document. It's called the DS 2019 for the 15 scholars. And the one that I had expired because it lasts for 1 year. And when it's only you have to apply it once every month. That is a minimum.
Yeah, it's like so. These sites might be said you try to use the faculty.
Let me go for the GS sound. The room I just go representative. But you can find it.
Oh, that's fine.
Yeah, they need one person, they will give you a fine. After 5 times, they come out. Yeah. But I was lucky enough that my officer was yeah, second generation Greek. And in the book, it says to the father from Greece. You look at his name, he had like Greek surname. And then was asking some questions and then asked my wife, do you know any Greek? I said, no, I need Greek. And yeah, okay, tell me when is your year? I saw some then he tells me this. You know that this is expired. We can get a
I should be starting soon as my committee shows up. Thanks for watching.
Close call. Because you get the family one, then we get you to the room, and then you know.
It's like all your stories end with some great
Yeah. Yeah. Although from what are the chances, right? So finally, what is with this capital? The capital is very likely to end up.
What was the last year?
But 10 million years. Usually when it's like AS, OS, or IS again, implement, it's probably not running curves. Let's do it.
They, I think I played trumpet with cataracts.
I'm very common and you're very busy. So he said he's free to celebrate me.
You would have come.
Yeah. Yeah, I told this morning, but I had my visa for 2 years. And also, from the way to Europe, we went through Canada. And very new for them.
Oh, what? In Canada?
Yeah, I was surprised.
I might go. Hey, see.
That's the opposite.
Thanks, maybe.
Exactly, this is what I was hoping that I would do show you in the tiger.
You remember Joseph? Back in SR?
Conservation office. So that you were taking over management roles.
Mostly monitoring around the team.
Wow, very high.
We're gonna do one chapter and learn my best. This is my former boss, mentor, Joseph.
Hello.
Microsoft, Steve.
Yeah.
So yeah, once the committee is all here, I guess we can get started. And people might trickle in ready to be observed. Yeah, thanks so much for being part of this.
Really enjoyed reading your dissertation.
Oh, great. Yeah, so it's gonna be a quick summary of everything. Good. And then this is Michael and Steve. Alex,
I'm Alex
from architecture, GSR committee.
Here, nice to meet you.
Okay, practice. Oh, we're going to have to do. Yeah. Change the rules. Yeah. Wow. Yeah. No, listen, Charlie.
Then I, now it looks
Oh, you know Raven? Oh my gosh.
I'm going to disappointed.
They gotta talk to. Yes.
And
Actually, Brian Johnson, I don't know if you know, he was the GSM before. Actually, more or less. But we deal with together on the computer. First time I've seen water.
can happen.
Waiting for Brian.
Yeah.
Finally.
Yeah, so just backstage pass. All access to the
All right, I think we have who we need. Really excited to introduce Aditya, who's attending today. It's gone for them, like 3 years. Lots of karaoke sessions on the beach.
Yeah.
But
real rock story.
yeah, yeah. fitting in.
Thanks a lot.
Again, wearing your tie.
What I'm doing every day, you guys do not notice. Actually, I had a tie and dye on earlier. So people on the webcast think I was going to wear that. And also not to go. No, just kidding. Very bad. So thanks everyone for being here. My thesis defense, Aditya Sankar. And my thesis title is Interactive In-Situ Scene Capture on Mobile Devices. And thanks, of course, committee for being a part of this. Really quick note, there's some coffee and refreshments in the back, so please feel free to help yourselves at any time. All right, let's get started. So today I'm basically going to be talking about architectural visualizations in various forms, particularly of indoor scenes. And these visualizations depict important aspects of these scenes. And there's generally like a few different kinds of visualizations that exist. A very common one is a 2D floor plan, picture something like this. And this typically is used for designing homes and offices. And it depicts very clearly dimensions, for instance, the length of the walls and so forth. The layout of the rooms, how they're connected to each other. And also structural elements like doors, windows, maybe some fixed appliances, and other things like the patio, garage, etc. So this is a very abstract top-down view of the scene and generally very useful for designing. Another common architectural visualization is a 3D model that's depicted here. This is a more faithful rendering of the scene. It's kind of like if you were there in the scene, what it would look like. It can include things like furniture, lighting, things outside like the background. It also captures the element of scene appearance. So it captures materials, textures, wallpaper, lighting, and so forth. So these two have been very useful for various different applications. And in general, humans like to know kind of about their space, both to record it, replay it, or essentially just like know where they are within it. So there's many different interesting applications. A few of them that come to mind are, of course, real estate. So for instance, if you want to buy a house or sell your house, wouldn't it be cool to be able to preview it in this kind of visualization very easily? Also, if you want to rearrange your furniture, instead of having to like lift up your heavy couch and bed and move it around, it'd be really nice to be able to do it, in this virtual manner and preview the results then and there. Some other applications include home remodeling. So if you want to remodel your kitchen, having sort of a 3D model picture of it beforehand would be very useful. Virtual museum tours exist. This is Google's art project that lets you walk around the Tate Museum, for example. And you can see there's a little like floor plan here that shows you where you are within the scene, kind of give you some context about it and so forth. And finally, sort of an offbeat application is actually crime scene investigation. So police and other people actually use floor plans to try and like place crimes and solve them within a space. This, for instance, if you can recognize, is actually the crime scene from the game Clue. Mr. White with a candlestick in the living room, so on and so forth. But floor plans have an interesting application there as well. Some sort of forward-looking applications of this kind of visualization. One is mobile robot navigation. This is a Roomba, for instance, that's like going around your house. It needs to know kind of where the couches are, where the carpet is, where the walls are, and so forth, to efficiently navigate. Home automation is becoming very popular, so having sort of floor plan of your house and being able to control lighting and air conditioning and security is another area of application for these kind of visualizations. And of course, augmented and virtual reality. So for instance, this augmented reality game, this character is jumping from the seat to the table to the floor. So the system kind of needs to know, what's the seat, what's the table, what's the floor, where are the walls, where's the user. So another potential application. And finally, for virtual reality, you're kind of like blocked away from your real world and just seeing a virtual world. But you can do things like have this sort of mesh or something called a chaperone that prevents you from banging into walls or into your couch or into your table. So there's multiple applications that can enhance the experience there as well. So digging a little back into history, these kind of visualizations go way back. This is a statue of Gudea from 2000 BC. It was headless when it was found. It's actually a prince who's sitting in this sort of serious position, and he has a tablet on his knee. And if you take a closer look at that tablet, it actually contains some floor plans of a temple he was trying to build for a god. So this kind of problem has been around for a really long time. A little bit more history. Draftsmen and architects have been doing this for a really long time. And the traditional tools have been, pen, paper, rulers, scales, protractors. and so forth. And of course, they've been doing at various scales and various levels of industry, both for like architecture and also engineering efforts. There's been a few significant advances, though, in this timeline of visualization. The first was a mechanical tool called the Universal Drafting Machine that was invented in 1901. That kind of combined the ruler, T-square, protractor into this one mechanical arm and made it really easy for a designer to create these visualizations by hand. Another big advance was Sketchpad by Sutherland in '63, where he used a graphical UI, like a pen and a screen, and some knobs to actually create these on a computer for the first time using the GUI. And finally, like modern CAD tools that started emerging in the '70s and '80s, but now are sort of everywhere, AutoCAD, Revit, and so forth, bring all of these features of CAD into this beautiful like software package, which are very full-featured and powerful. So with each step, there's been like a sort of a significant leap in the productivity of these designs and of these visualizations. So just a bit more about CAD tools. There's an issue with them, though. They're generally pretty complex and difficult for non-expert users. That's actually a book called Learn AutoCAD Basics in 21 Days, and it's pretty thick. And 21 days, like I'm not going to spend 21 days to learn AutoCAD to build a model of my home. So it requires significant like manual effort and work. And they generally design for what's called ex-situ use. So you have a scene and you have a desktop computer elsewhere. And you kind of record measurements from the scene, a ruler and notepad, go to your desktop, and then you recreate that. So, reproducing these renderings faithfully is kind of hard. So the question I'm asking is, how can we lower this bar even further? In other words, given this timeline of progression of tools, like what's next? And to sort of answer this, I asked you to think about two key insights that I've had during the course of my dissertation. The first is to use this revolutionary tool. Of course, the mobile device exists in various different forms, and it can be used to like change and progress every day. They possess very rich sensing capabilities, all kinds of sensors, cameras, and so forth. They're ubiquitous. I'm pretty sure everyone in this room probably has one in their pocket right now. And they also allow for familiar interactions like touch and movement. So, you can actually move around with them in space. You can use a touch screen, which is very intuitive. So I think there's something really interesting in this line of devices that can be tapped as the next wave. The other insight comes from this rather stern-looking gentleman. His name is John Tukey. He's a very famous mathematician and statistician. And he had a quote that I thought was quite inspiring. So he says, "Nothing, not the careful logic of mathematics, not statistical models and theories, not the awesome arithmetic power of modern computers, nothing can substitute here for the flexibility of the informed human mind. Accordingly, both approaches and techniques need to be structured so as to facilitate human involvement and intervention." So somewhat controversial statement and very sort of assertive in that, combining the computer and human can really sort of enhance things a lot. So I think there's some truth to this, especially sort of from an HCI background. I think designing things as a tool for the user can be very, very powerful. So I took some inspiration from that and thought of essentially like a semi-automated approach. So combining the strengths of both the user and the computer. So for instance, if I ask a user or a human to like identify what this object is, it's very obvious that it's a table. And actually, most computers these days can do this as well, pretty efficiently. But let's say, a picture like this, where there's a little bit more clutter, there's some pictures on the wall, there's some occlusions, there's a window, some reflections. Computers are still, trying to figure out, what object is within that efficiently. And, to varying degrees of success. But if I ask a human, they can easily tell me that that's a chair and an ottoman. And they may even know further details, like the fact that it's an Eames chair and an ottoman. So the human is very good at high-level reasoning and high-level tasks that come very naturally to us. However, if you ask a human to solve this kind of combinatorial like optimization problem, it'll probably take us much longer. But for a computer, this is actually trivial. So the insight is, can we combine the best of both worlds to achieve our task? So with that, having a human in the loop, there's a few advantages. So these indoor scenes are challenging, especially because of textureless surfaces and reflective objects for computer vision algorithms, but humans aren't easily fooled by that. So the user can provide these semantic cues and they can correct mistakes in the scene. And finally, they're in situ, so they can move around, they can interact with the scene perhaps, and they can capture various info. So the idea of this thesis essentially is to enable non-expert users to create useful architectural visualizations in real time. And the two insights are to first replace the canonical measuring tape with a mobile device, and second, to involve the user as a guide for reconstruction and recognition algorithms. And in this talk, I'll talk about 3 projects that try to achieve this goal. The first one is capturing room layout with iPhone. And the idea here is to use just a regular smartphone, walk around your house for a few minutes, be able to capture a virtual tour, a 2D floor plan, and an empty 3D room model right on the device. The second project I'll talk about is sketch-based 3D modeling using an iPad. So you essentially take that empty room model, you could use your iPad and like sketch in objects to create kind of a 3D model of your scene. And finally, I'll talk about a project that improved the room capture process on Tango, which is a 3D-aware mobile device, which I'll talk about in a little bit. But the idea here is to capture more complex scenes faster using the power of 3D-aware devices and deep learning. So really quickly, I want to put my work into some context and talk about some related research that we worked upon. So 3D reconstruction modeling has a very rich history in research, and there's a whole spectrum of different approaches, from automatic approaches that don't require any user intervention, but they generally tend to be brittle, and again, because of textureless objects and reflections, they tend to break a lot. And they also usually lack semantics, so they discard information about what's a chair, what's a floor. They just consider things as objects in the world. And the other end of the spectrum are fully manual, which generally include CAD tools and other things that have a pretty steep learning curve. They're often tedious and require a lot of manual effort. But as an advantage of having a user in the loop, they generally have semantics. And there's a slew of hybrid approaches in between. So just a quick overview of some automatic approaches. There's image-based reconstruction that takes a bunch of images and reconstructs 3D models. It works well outdoors for things like the Colosseum, but it works poorly indoors. It generally lacks semantics, and it has holes in the geometry and other issues of incomplete reconstruction. Class of methods called depth-based reconstruction that uses a Kinect camera or similar depth-based devices and fuses them into a single point cloud. And this generally forms these large, non-semantic polygon soups, which are hard to edit or move around or transmit. And they're usually tedious to capture because you take this device and sort of scan every surface of the room for completeness. And there's the third category of sort of automatic methods are image or depth to CAD model. And this is sort of the closest to the proposed approach in this thesis. This uses a database of models and then images or a depth sensor to try and extract sort of the closest matching CAD models in the scene, and then try to reconstruct like a room, for instance, using those CAD models. But most prior approaches to image or depth to CAD have been ex situ without any sort of user in the loop or any kind of user in the loop. I won't say much about manual approaches, except that we talked about CAD earlier, and most of the work here is on carefully designing these interfaces to make them as user-friendly as possible. And finally, some hybrid approaches. There's a whole bunch of work on sketch-based retrieval, where you essentially draw a freehand drawing of the scene, and then from a CAD model database, you sort of pick the best objects and reconstruct the scene. However, it's pretty hard to draw these freehand things accurately, so we can probably do that. And then finally, there's some work on in-situ modeling that kind of you're located on site with a tablet, and you kind of look around and you sketch in free space. So our work kind of like is a combination of these two overall insights. I just want to highlight a couple of more pieces of related work that have had particular impact on mine. So this is some work from Furukawa and Zhao et al., where they reconstruct indoor scenes but use some priors, so some prior knowledge about indoor scenes. So the key insight here is that most indoor scenes are dominated by axis-aligned planes. So for example, this room has planar walls and corners that meet at 90 degrees. So can we use assumptions like that to simplify the problem and solve it successfully? So for instance, this is an indoor scene, and that's a museum that's been reconstructed with these prior constraints in mind. And the other piece of related work that I've heavily used here is large set of CAD databases that exist online. So there's various research and commercial efforts that catalog CAD models of objects. For example, ShapeNet and SketchUp Warehouse. And just for instance, ShapeNet has about 3 million models, of which 220,000 are classified into 3,000 categories. So it has like a large library of objects that exist in the world, real. So, maybe we can like leverage that to reconstruct these models more efficiently. So just a quick summary again, this thesis, replacing the tape measure with the phone, involving the user, using priors and simplifying assumptions about the furniture. And generally, the approaches that I have proposed are hybrid, but they try to progress towards automatic with each project. So it tries to sort of move in that direction and make it easier for you. So to start with the first project, this was presented at WIST in 2012. It's about capturing room layout with iPhone. And I talked about the brief overview of using a phone to capture a tour and then a model, but it's much better explained with a demo. And most of my work is sort of in the practical and application side, so every project will have sort of a short video that you can watch. So the idea here is the user walks into the room, pulls out the phone, and launches the application. They stand in the center of the room and essentially like rotate around the room while capturing image data. Along with the images, we also capture the orientation of the phone, like the heading on top. And so the user sort of captures this panorama. Once the panorama is complete and the user reaches the starting point, the system automatically detects this and tells the user to move towards the next room and swipe up. So the user aims towards the next room and swipes up and walks into the next room. So this is like the essence of the capture process. After they reach the next room, they simply like swipe down to indicate that they've completed the walk, and they restart the panorama capture process. So with this, in a few minutes, you can have this sort of visual tour of your scene, similar to like Google Street View. You can interactively look around each room. And you can also move the phone around to sort of get a window into that room if you wish. And then if you aim towards a door, the system remembers where that transition happened and will actually show an icon of an arrow moving in towards the next room. So if the user taps on this icon, you actually just do the smooth walk between rooms. So in this way, you kind of get a sense of the space and how things are arranged. And again, in the other room, you can look around interactively as well. A really exciting feature of this work is that you can create a 2D floor plan from this data, and also empty 3D model. And how we do this, I'll talk about really quickly. So during the capture phase, again, you rotate the phone, and as you're rotating, we capture image data, and also capture things like the yaw, pitch, and roll of the camera from the gyroscope. So we use the yaw, which is the major axis of rotation, to index each image, and then we replay it interactively in the next step. So the playback so the panorama is played back interactively with the orientation. And then you can either use touch or movement control. We remember the positions of the door, so we present this arrow to transition, and we touch the arrow. It's a sort of a simple temporal video that connects to it. So the interactive modeling process that we use to reconstruct the floor plan goes something like this. So it involves some basic user interaction where the user marks some features in the room. And then we can reconstruct the shapes of the room and the layout. Users marking the edges of the walls, so like kind of where two wall corners meet. And this here is a visualization of a top-down view of the scene, where the blue dot is the user, and each edge is kind of a direction in the scene. So this is the second wall edge, and when the user confirms that, the second direction in the top-down view is shown in that diagram. The user can also mark doors, which are sort of designated by two edges, one for each end of the door. And they also tap sort of the room connections. This connects to the kitchen, for instance. The doors are shown in yellow, in sort of orange color in the top-down view. So after this sort of quick modeling process for each room, we end up with this kind of result, where we have a top-down view of the scene, blue dot being the camera or the user, and the green lines being directions to the corners, and the orange line direction to the doors. However, this is not enough information to reconstruct the floor plan, because there's a few different possible rooms that can form with these constraints. So for instance, this room has all these corners in the right spot and the door in the right spot, but clearly doesn't look like a real room that exists in houses usually. And this is another example. So we go back to the thought about the Manhattan wall constraint, that most houses and floor plans follow the sort of right-angle planar structure. So can we use this assumption to simplify this problem and solve it? I will note, however, this doesn't work on all buildings. Frank Gehry, for example, hates my research, and so this is a simplifying assumption that does not work in all cases, but works in a significant majority. So really quickly, I'll show the algorithm that's being used to reconstruct the floor plan. So from arbitrarily picked first ray, we pick a point P1. And from P1, we draw a hypothetical wall at angle alpha1 to point P2 on the second ray. Point P2, since we're using a Manhattan wall assumption, there's only two possible wall orientations. Either one goes 90 degrees upwards or 90 degrees downwards. So something like this or this. And this is easy to discard the invalid one because upwards there's no other corner that will intersect with. So we go down and intersect the third wall at P3, and then we continue this process. So P4, P5, turning 90 degrees at each time, P6, and finally we get back to our original corner, P7. You will notice, however, P7 and P1 should actually be the same point, except in this hypothetical scenario, they're separated by some distance d. So the problem here boils down to minimizing this d by changing the initial guess of alpha1. So we run a really quick optimization on alpha1, and then find alpha2, which actually minimizes that distance between P1 and P7, makes them the same point. And in this way, we reconstruct Manhattan floor plan. To estimate the door position, we take the orange rays, and we intersect them with the walls, and we get 2 points that depict the doors. And remember, we know where that door connects to as well, and we have the same door from the other side. So what we need to do here is for room 1 and room 2, if these red dots were corresponding doors, we just need to rotate, scale, and translate such that they sort of jigsaw and fit into each other. And you essentially get your floor plan layout between rooms as well with this method. So some quick results. This is ground truth that I measured by hand. This is results from the app that created in about 7 minutes. And this is an overlay comparison. As you can see, it's not perfect, but for the fact that it's from a phone and in 7 minutes, it's actually very good and compared to state-of-the-art methods. And there are some issues here. For example, the wall is recessed and it isn't in this case. And there's 2 doors in this room, whereas our system only supports 1. But there was a manual editing mode which allowed you to fix it. Another example of a house, there's a little failure case here that I'd like to point out. This house had a bay window, so like a window that extends a little bit out into the outside. And since this is not a Manhattan structure, our system approximates it with just a planar wall. So it's a small sort of deviance from the ground truth, but worthwhile. So the contributions to this work were an end-to-end system to visually capture these indoor scenes in terms of a tour and a floor plan. It runs in real time on an iPhone 4, which is a very basic, cool smartphone, so it can run on very minimal hardware. And again, quickly and easily capture these floor plan layouts and 3D models using just mobile devices. So from the 2D floor plan, we kind of extrude them into the 3rd dimension, and we can have these empty 3D room renderings, which is kind of interesting because there's some potential here. So this inspired the next project, which was sketch-based 3D modeling with an iPad. So we moved to a slightly bigger form factor, which is an iPad, so you have some more room for interaction. The empty 3D room model that was presented at the end of the last project is actually in here as an inset. So this corresponds to kind of a live view of the scene that you're seeing through the camera. And the user can have sort of touch and talk interactions. So again, to describe this a little bit better, so similar to the previous project, the user rotates around the room and captures the corners. In this case, sort of as they go, a little bit quicker and easier. You can see the little flash from that. And then this empty room model is reconstructed similarly to the last project with some improvements. So this room model is shown here in the corner, and this is a live view of the scene. And as you can see, as the user moves around, they both correspond to each other, and the system is tracking where the model is moving. The user is kind of standing in the center of the room. To add objects, they push the top button and say the name of the object, like table. And then the system freezes, and the user just sketches the outline of the table. So given the model and given the sketch, the system retrieves the 3D model and places it into the scene. And the user can do things like, say, replace it with an IKEA desk, which is the type of desk in this room, and the model gets updated automatically. They can also do things like add computers or lights or desk clutter in this case to the scene to give it more realism. Another example of a chair, they say chair, it freezes, they draw the seat, they draw the legs, and they draw the back. And as you will see, a chair will be retrieved from the database and placed into the scene. at roughly the same scale, position, or orientation. And in this case, it's an office chair or air-on chair, so they can replace it with whatever furniture they have in their environment. So this way, they can go on and construct each element of the scene that they're interested in. So other things that you can capture with this are also like doors and windows. So for instance, for a window, you just say window, and you draw the frame of the window. That will be demonstrated here. And this is a blank wall, but then the system recognizes that the window has been drawn and places it into the model. You can do things like add curtains or other accessories on previously placed models. So in this case, the user adds curtains to it. The next aspect was adding artwork to, again, add a layer of realism to the scene. So again, similarly to a window, you sketch the frame of the artwork. But in this case, we extract an image from the real scene and place it in the model. So you actually get, your textures in the scene as well. One more example. And so just 2 strokes and a very simple way to transfer artwork into the model. So how does this work? This is, again, based on a simplifying assumption of a furniture prior. So the observation here was that most pieces of furniture generally have structural components that are either planar, vertically, or horizontally. For example, a chair has a back. The insight here is to take a database of these models and manually extract the skeletal structure of these models by drawing lines. And these lines, the ones in green are vertical, and the ones in red are horizontal. So most pieces of furniture, like tables, chairs, beds, sofas, can be approximated in this way. Again, not all, but a significant number of them. So this is just like some examples of our database where dressers, cabinets, couches, beds have been extracted as skeletal models in this way. And our database consists of about 60 pre-processed models. The next question is, how do you take that sketch the user drew and find the model that fits? So in this case, the user starts with the vertical line, which is depicted in green. Given that we know the position of the camera and the orientation of the user's hand from the gyroscope, we can essentially project the sketch into the virtual scene, which we also know from the empty room model, and intersect this vertical line with the ground plane. That looks something like this. And this vertical line forms a supporting line of height h at some point in the ground plane. So every line that's connected to this vertical line is then projected into the scene and is again supported by the line h. So this horizontal line translates to this horizontal line in the 3D scene, again in height h, and so forth. So once the sketch is over and we have our 2D to 3D projected sketch, we then do a search through our database with an exhaustive 3D ransack algorithm, more details in the paper, and try to find the 3D model skeletal structure that best fits the sketch. In this case, it's actually a pretty simple structure. It's 3 lines. So a table actually fits this model very well. So we need to essentially move the skeletal structure of the CAD model to fit that of the scene. And when you do that, your CAD model gets placed in the scene. Similarly, for things on the wall, like windows and artwork, the vertical and horizontal lines are projected, but this time onto the wall plane. So you get sort of a structure on the wall. And similarly, with the search algorithm, you can scale, rotate, and translate your models to this step. So some results. On the left is a real scene taken as a video, and on the right is the same video of a virtual scene that's been captured by the user. As you can see, it captures various elements like tapestries and beds and windows, etc. This is like an office scene. It's actually Steve's office, and add computers, plants, and other elements into the scene.
Brought my plan back.
Yeah, is it not there anymore?
No, it's Steve's.
So yeah, some more results, and it generalizes to other scenes like bathrooms and offices and bedrooms and so forth. There's more results. So once you have this sort of 3D model, what do you really do with it? And this goes back to the applications and initial motivation. So in this case, the user is actually sitting on their couch and using the iPad application to move around the furniture virtually, so they can rotate and translate the furniture. And once they want to preview it, all they need to do is lift up the iPad like they were looking into the real scene, and the system sort of flies into your 3D model and looks around. So this is only possible if you have the semantic representation of the scene as a CAD model, which I think is the power of this technique. And again, this model was captured in probably about 10 minutes or so. So you can get sort of very interesting applications from that. We did do some comparisons with other systems that exist. Homestyler, for instance, is a system that is a web application, allows you to create these models by hand. And it produced very similar end results as ours. But we found that ours essentially was much faster, mostly because manual measurement was not required. However, as a trade-off, you may deviate a little bit from the ground truth. So the contributions of this project was this design of like a multimodal interface for in-situ indoor 3D model capture. And these algorithms retrieve these 3D models in real time from sketches. And as an end result, the user gets these editable 3D models of scenes for rearrangement and visualization. This project did have some limitations though. Since it was on an iPad and the user was stuck to like one point, there were some tracking errors. You'll find like the cabinet didn't quite match the cabinet of the scene. There may have been some sketching errors. So a small error in the sketch will result in a sort of an error corresponding in the 3D model. There may have been occlusion. So for the center point where you captured everything, you may not be able to see the table. So the user can't really sketch that completely. Also, our database was somewhat limited. It had 60 models. And if you can keep expanding that, but there was not a manual effort involved. So there was room for improvement. And this inspired the last project, which is improved room capture on Tango devices. And this is going to be presented at WIST in Canada in a few months. So the key idea here is to leverage two emerging technologies. One of them is a 3D-aware mobile device, in this case, a Google Tango phone. And the second is major advances in deep learning. And this is some related work from Lee et al. Of retrieving CAD models based on images. So I'll talk really briefly about these two. So this 3D-aware mobile device actually is very interesting. So it can track itself in 3D, rotation, orientation, and all, and do things like add virtual objects into the scene. So you get this kind of augmented reality experience. But one other thing it also does is it can tell you the distance of each pixel from the device using a depth sensor, which is located in the back of the device. So really powerful for creating experiences like adding new things to the scene. So we are kind of using this for our purposes of capturing existing objects. The other work is deep learning on 3D model databases. So given these large databases like ShapeNet and so forth, there's a way to train the models to use input image of the scene and then retrieve like matching models. However, you can see, it's not a perfect system. It gives you the top end results. So in this case, it's nice to have a user to come in and correct mistakes. And also, like if the images have a lot of clutter or occlusions, this works. The success is even lower. So that inspired this project on improved room capture on the Tango device. And again, there will be a quick demo. All right. So this is a scene that was captured with this application. So it took a few minutes to capture, and this is actually the end result. So as you can see, you're looking at a 3D model of the scene overlaid over the real scene, looking through this augmented reality window. And the system captures, chairs, tables, couches, windows, doors, things on the wall like artwork. And it's fairly accurate at capturing various, this is like a specific kind of chair, and it's different from the chair in the back. So it works in quite a general sense compared to previous work. And it gives you a really interesting model and a good sense of the scene in a few minutes. So this is kind of how the scene capture works. The user first aims the device at the floor, and then at the ceiling to capture the dimensions. And then to capture the walls, you follow a similar protocol as previous projects, where you sort of mark wall edges as you go. So the user just simply aims at the wall edge and taps, and then moves along to various wall edges in the room. As you can see, this green mesh visualizes kind of where the walls are being recorded. So pretty simple process. And in this case, since it's a 3D aware device, the user can move around and get around occlusions, capture concave corners and so forth. Once they get back to the original corner, the system snaps the room shut and forms a solid shape, and then moves on to the furniture capture stage. To capture furniture, the user taps on like a dominant surface in the furniture. For example, for a seat, it's for a chair, it's a seat. Stands back and takes a picture of the chair. In a few seconds, a list of results is returned of matching chairs, and the first result is placed into the scene at the correct position and orientation. So in this way, the user goes around and snaps in objects into the scene. This is another example of a chair where you capture the seat, you simply stand back, you press the chair button to take a photograph, and in a few seconds, a list of results is returned, and the first result is placed into the scene. Now, in this case, the result doesn't quite look as good because of issues with the learning algorithm. So the user can actually go in and correct it and pick the best result, in, for instance, this one. And that gets updated and placed in the scene. So in this way, the user can go around and build these models of the scene really quickly with one tap to select the surface, stand back, take a picture, a few seconds, and then you can move on to the next object. So you can also capture tables. However, as you can see, like the field of view of the camera is not enough to capture the table in one shot. So the user can use multiple taps to like add on to the surface. And again, they can move around freely in the scene. And once they're satisfied with selection, they can stop and then take that picture. So this looks pretty good. The user is going to stand back and take a picture of the table. And then from the 3D model database, matching tables, what the algorithm thinks are matching, are returned, and the user can select ones that suit the scene the best. So in this way, within this augmented reality platform, the user can just like look around and capture these models really quickly and really easily. And they can preview the results as an overlay or even as a 3D model. To capture windows and doors, we have a similar scheme where you mark the top right and the bottom left corners, and this sort of box is drawn over the scene. The user then indicates if it's a door, window, or artwork. In this case, it's a window. And a list of windows is shown at the bottom, so the user can select the one that best matches the scene. And similarly for doors, they mark the top right and bottom left corner, indicate that it's a door, and pick the best matching door from the scene. And finally, they can preview their 3D model in real time. We also have a method of capturing artwork here, similarly, top right and bottom left. In this case, when you indicate that it's artwork, it tells you to take a picture of the artwork. So you stand back and take a picture. It again gets extracted automatically from the scene and placed into the model for later view. So some results of this technique. This is the living room with bay windows and with glass doors. And this technique works a lot better. And this is a 3D model representation of the scene that was captured in a few minutes. So really briefly about system architecture, there's a lot more details in the paper, but I'll talk about a few key components. First one is to capture the furniture surface and how that works. Second, I just want to mention really briefly that there's a server in the backend that has various different convolutional neural networks that have been trained on many thousand examples of chairs and tables. So for example, ShapeNet has 6,000 chairs, 8,000 tables, 2,000 sofas, and so forth. So these machine learning algorithms are picking the best, top 5 or top 10 from a very large set of possibilities. And finally, once the best possibility is returned, how we place that in the scene is another aspect I will talk. So to select the plane, we extracted dominant surfaces in the furniture. And we found the observation here was that things like tables, chairs, beds, other pieces of functional furniture generally have a surface that's horizontal and dominant. So for example, for a chair, it's a seat. For a table, it's the surface on top. For a bed, it's a mattress, and so forth. And the reason for capturing this is that it gives a really good sense of the scale, position, and orientation of the furniture from just that surface. So the user extracts this sort of surface by tapping on the surface itself. And we use a rotating calipers algorithm on the depth information, and there's more details in Seamus's PhD thesis about it. It's a very simple algorithm that takes points on a 2D plane and finds the best fitting non-axis aligned rectangle that explains those points. So in that way, we can extract sort of the rectangular surfaces of these objects. And we call this a user marked surface. So this is the one the user has extracted from this. Now, given the machine learning algorithm has given us a matching CAD model, how do we find a similar surface in the CAD model? We do this automatically. First, we cast rays virtually into the CAD model, the same way a depth camera would into a real scene. And we produce a point cloud of the model as shown there. And then we run a similar rotating calipers algorithm to find the dominant planes in this object. And we call this the model extracted surface. And this step occurs automatically on the device. So the problem here is to essentially align the user marked surface and the model extracted surface. So in this case, the seat of the real chair and the virtual chair have been aligned. And when you get the alignment, you actually find that the model is rotated, scaled, and placed in the correct position in the scene. So that's the key idea here. However, this is an ambiguous case because in this case, it's a rotational ambiguity. So the chair is actually facing off to one direction, but the plane is square. So there's 4 possible orientations that could be explained here. However, we have a scoring function that tries to solve this. So the dots that you see here are for each point in the model, whether or not it is explained by data in the scene, so it's actual depth information. So on the seat, for example, some points are being explained by real points in the scene, but the back has not been explained at all because there's actually no back of the chair. So in the case of a chair, there's sort of 4 cardinal directions that we can test. And we find that one of them has a much higher score than the others. So for example, in this case, many points on the CAD model explained by points in the scene. So we can assume that this is a much better fit for the scene. So the green points in this case indicate a much better fit. So to evaluate this interface, we conducted a user study with 10 participants who had never used the system before. This is a within subjects design. They use Homestyle, the tool I mentioned earlier, to do this on the web, and our In-Situ tool. And the study consisted of a demonstration by the researcher, some familiarization by the user, and then finally evaluation. We randomly assigned half of the users one of the systems first, so there's no carryover effects like fatigue or practice. And then finally recorded things like time, placement accuracy, and collected some qualitative feedback. The task here was to again model the study room, which consisted of 4 distinct chairs, 1 table, a window, and a door. And this was the sort of setup, and this is a sample output that a participant could use. The results of the study were actually really interesting. We found that the task time is significantly reduced for our system, which is in blue. The system that we compared to Homestyler also required manual measurement of the scene to enter wall dimensions and so forth. So that's indicated in a different color. But even if we ignore that, our system was significantly faster. Also, we calculated a placement error in the form of a Jacquard index. Details about the numericals are in the paper. But we found that we are significantly more accurate as well in the other system. So the study confirms our hypothesis that the system of In-Situ capture is both faster and more accurate than the traditional desktop ex-situ method. So a quick visualization of the placement error. So what you're seeing here is actually a top-down view of the scene. The lines in green are ground truths, so a captured point cloud of the scene where I've annotated chairs, tables, and so forth. And the lines in red are captured with the tool. So these are the top-down bounding boxes of the chairs, tables, and also the walls. So in this case, this is a comparison of our system. You can see the red captured by our tool is very close to the ground truth, which is in green. And this is a comparison with Homestyler, where there's much more significant deviation, both in terms of the contours and centroids of the objects. So we do much better in accuracy as well. We also collected some qualitative feedback. So we asked the users what they thought about the mental demand, physical demand, temporal demand, effort, and other axes of qualitative analysis. And the results in green indicate that our system was much lower, and results in red indicate that it was much higher. So the general overview of this graph is that almost for pretty much for every axis, the user found our system to be much lower, slightly lower in these demand axes, and also in terms of qualitative feel of error, both in appearance and position, which were confirmed numerically as well. Some quick quotes from the study. The users said things like, "It was a much smoother process, and I was more confident in the result. Being able to quickly preview models in place was a huge benefit. Finding matching furniture was easier, and no measurement was required." So that was really encouraging. There's some positive feedback. There's also some feedback for future improvements. It said things like capturing large surfaces was frustrating and inconvenient at times. Holding the Tango up in front of you for several minutes can be tiring, which is interesting feedback. And finally, making manual edits was not possible. So it was one of the most requested features, slightly adjust things manually after they get captured. Some more visual results, and over here there's sort of 2 columns. The first column here shows a picture of the scene taken with the camera. Second is a corresponding view of the 3D model. and a top-down view for 6 various scenes. As you can see, it sort of captures a good representative layout of the scene for rearrangement of visualization purposes. So the contributions of this project were extending this in-situ modeling approach into 3D-aware devices, a new class of category of devices. Creating and designing system architecture to combine the 3D-aware user input, like things like an object recognition, to successfully produce this sort of 3D model output. And finally, a study to compare and evaluate the performance against traditional tools. So to conclude, just a few thoughts. Hopefully, I've motivated the problem of creating these in-situ semantic scene models is interesting and useful for various applications. And then I presented 3 projects that leverage mobile devices of various types and in-situ interaction to produce interesting results. So the 3 projects I talked about was capturing room layout with iPhone, and this was to capture a virtual tour of the scene and a floor plan and an empty room model in a few minutes, with just some basic interaction. And that kind of laid the groundwork for the rest of the projects, which sort of showed that in-situ interaction was indeed useful. The second was sketch-based 3D modeling using an iPad, so a larger interactive surface so the user can look around and like zap in objects with simple sketching. And it produced very interesting results and certainly had some limitations, which inspired the third project, which is improved room capture using Tango and future 3D-aware devices, which made sort of capture of more complex, high-fidelity models both faster, easier, and more generalized. So where do we go from here? So for some future work ideas, I think it would be really great to relax the constraints that we had set to simplify these problems. So for example, these 2 buildings have curved walls, non-right-angled corners, so AKA the Frank Gehry problem. And actually, it's very interesting to note that there's a group, particularly in Italy, Pintoré et al., that has extended our work into this domain of in-situ mobile capture to try and solve these problems. So there's some interesting directions here to be explored. The second is to relax the constraints on furniture and add more categories and more sort of general aspects of furniture. So in this image, for instance, our system can probably capture the chair, but the plants are sort of these amorphous, non-planar objects. So there may be ways to capture them, and there's been some work on using volumetric convolutional neural networks to essentially like train on 3D models and then given depth information, try and extract the best matching model based on that. Adding more categories of objects, of course, like lamps and refrigerators and other things would be great as well. And finally, I think it would be interesting to try and morph the CAD model to more closely match your scene. So if you have a chair that's slightly different, you get sort of a better result. And there's a lot of related work in that direction. Most of the projects so far have sort of, there's a big room layout, and then you go into each room and you produce a single room model. But it'd be really nice to have this kind of like full dollhouse style view of your house, including subtle things like texture and lighting, things like wrinkles on the bed sheets. So if you can get this kind of like really rich and full-fledged 3D model, I think that would be really useful and really interesting. Extending my system to head-mounted devices would be really interesting. So if you remember, people said it's very tiring to hold a phone in front of you for a long period of time. But the head-mount system kind of like sits on your head, and you see the virtual content overlaid over the real scene. So there's not as much fatigue involved with holding a device. So HoloLens is one example where this kind of work could be used to like read these models, but like right in front of your face, like it's interacting with the scene in real time. And actually, I worked on a quick demo to demonstrate some potential of this technique. So this is actually captured from the HoloLens. So you wear the device, you press record, and this is what I was seeing through the device. And the idea here was to essentially like scan the room for, in this case, chairs. And I've only included one chair model. But as you scan the room, it finds where the chairs are and tries to place the model in the correct spot. And the user sort of taps with their finger to like, confirm that location. It also does things like rotate the chair to the right position and orientation. So in this way, the user can like just look around the room and like zap in objects. And hopefully, in the future, all different kinds of objects, not just chairs. But this shows that there's some promise in this technique. And in fact, this makes it very easy, fast, lightweight, and interesting to do. So in this way, the user can capture the chairs, and now you can pull this into a VR game or an augmented reality experience, and you have the furniture in the scene in just a few seconds. And looking much further forward, I think it's very exciting that this kind of work should and will, I think, expand to millions of devices. So there's been recent work from both Apple and Google to create software development kits like ARKit and AR4 that brings augmented reality and full tracking to a bunch of devices. In this case, I think ARKit will work on legacy devices to the number of about 380 million and growing. And AR4 will start with 100 million devices that can do this sort of in-situ like tracking. So I think the techniques proposed in this thesis can scale easily to these kind of devices once these SDKs become popular and effective. And also, I think there's many in-situ interactive applications, both in terms of architecture, but maybe in terms of education or even health that need to be explored in this area. So I think it's a very exciting future for this line of work. So I'll wrap up with some quick acknowledgements for this work. So of course, Steve has been an awesome guide and mentor throughout the whole process of this PhD. And a lot of the ideas here are a collaboration with Steve. And I think something that he always told me is to like try and think of a magical solution, something that seems really intuitive and like, oh, how did that happen? So I like to think of Steve as my personal wizard. He also taught me how to take some great selfies and some terrifying face swabs. So thanks for all the advice, Steve. I'd like to thank the committee for their participation, Brian, Michael, and Alex for being here today, and then Linda and Brian Johnson for participating in my generals committee formally. A quick acknowledgement to the Grail Lab. This is the graphics group at UW, and this is a picture from a retreat we had a few years ago. Some really awesome, interesting, and amazing people, great collaborators, and particularly the people who helped rehearse this talk and also edit my dissertation. Quick acknowledgement to my Seattle friends, some of whom are here, and they've been my family while I've been in Seattle. And also to my mom and dad, who are hopefully watching online. Hi, Mom and Dad. They're not pictured here, but they'll be here next week to hang out and check out Seattle. So thanks to everyone. And finally, thank you for being here, and I'm open to any questions.
Cool. Maybe open it up to questions from
in your opinion, what is the something that's from an automatic or what is the main disadvantage of using like bandwidth fusion or fusion type of work?
So I think there's been a lot of interesting research in that direction. I think the solution kind of lies at starting at a hybrid approach and seeing what subproblems are interesting and pushing automation by like guiding the research using those sort of human intervention things. So I think like vision-based approaches, the main disadvantage is that they discard any semantic information. But then there's interactive methods now like semantic paint, if you've seen, where the user like walks around and then touches various objects and introduces semantics in these models. So I think there's sort of it's not quite clear what are the problems that need to be solved to do this automatically. So having the user like define those problems and maybe correct errors is an interesting way to like try and find those research problems. But in the future, hopefully, this is something that will happen fully automatically, where you just like literally walk around with like scans and create these models. But at the moment, I think the biggest thing is this lack of semantics. So you can create these models, but they'll just be like polygons. They won't be like chairs or tables, and they won't have back sides or undersides. So I think there's some work to be done to make this fully automatic. But it's an interesting area for sure.
All the examples were for architecture and consumer focus, but it seems like it's applied like CSI or something like that.
Yeah, I mean, I think there's various different commercial applications, and then part of my work was actually extending this and forming a business plan and trying to like figure out this application. Turned out like insurance is one of the very interesting things that people want to like catalog their space, annotate all their objects, and not have to do it by hand. And of course, like search and rescue, fire departments, accessing floor plans to City Hall is much harder than if you say everyone has like, an online floor plan system. So there was very, interesting ways to try and commercialize this work, and it's actually part of a business plan competition for a while. So I think, there's very, varied applications beyond real estate. Real estate is the kind of the most obvious one that people are ready to like buy this like right now. So I explored that the most. But I think there's CSIs are a bit more on the fringe, but I think still pretty useful. Insurance and fire departments and other things. And I think museums and like heritage capture could also be very interesting. We had worked on like capturing heritage in India using various technologies, but everyone has a phone and can capture their favorite like small temple and have a big catalog of this.
Yeah. Have you talked with like roboticists or seeing construction researchers about how you can use this to really get it?
Yeah, so I think that's something we've considered, and it's something that will happen if this scales to like thousands and thousands of users, because if everyone captures their homes, you then automatically have this data set of like where objects are placed in relation to each other, scales and arrangements and so forth. So we've considered that, but I think the roadblock there is just to scale this commercially to like, thousands of people. But yeah, I think that's something that's very interesting that we have actually talked to people about forming this kind of training data set. But yeah, future work hopefully.
Questions? All right, so why don't we move to the committee sessions on the committee or the faculty members? Welcome to the department.
Thanks for coming, everyone. Thanks, guys.